Morning, good evening, guys. Welcome to another episode of Xan Talk Show. We are going to code Wolfram Language today. This is a coding session, so it's just going to be me coding technical stuff, Wolfram Language. Okay, so because code, you need to code non-stop coding. Wait, what's going on with my Emacs Windows? Wait, there is something. Yeah, so part of the window is not showing Emacs. That's what. Okay, coding session today, Emacs Lisp. Okay, so not to do. Let's go to talk show. Today's talk show. Open it. So Wolfram Language coding session. We're gonna write a custom function to export SVG graphics. Now we did several talk show before a week or 2 weeks ago. So the last one is episode 697. We explored how to do this and we aborted because it seems too difficult. But I decided we're gonna persist. Okay, so we're gonna persist to write this function. This is for exporting graphics, exporting two-dimensional graphics to SVG. Now, if you watch my previous video, episode 697, and then another one, episode 687 in July. That one is very technical. That discussed why we need to do it and so on. So, we talked about SVG, the technology of SVG, which is XML file, and lots of issues. But anyway, so we're gonna just code, okay? So if you don't know Wolfram Language, I have many videos. So you can download it here, search for Xali Wolfram Language tutorial for programmers on xali.info, okay? And you can find the download link. It's free for personal use. And Wolfram Language for programmers, a comprehensive tutorial for programmers if you already know a programming language, and lots of my Wolfram Language packages. I've been coding Wolfram Language for like 30 years. I discovered that both of my physics, let's see, let me magnify the font, Control plus, okay. Let's see. So this is boring for you guys, for most of you guys, vast majority. This is just me coding Wolfram Language, because, this is lots of technical details. I won't be able to explain each one of them in detail, so it's just watching me code Wolfram Language, okay? I'll explain something along the way. So if you already know Wolfram Language, you started to learn, maybe for my tutorial, then, maybe you coded Wolfram Language for half a year, then you'll know what I'm talking about. But for most of you, it's probably boring. And if you are watching this offline, best to play at 1.5 speed, okay, minimum. Hexar discovered that both of my physics teacher love Wolfram Language. Oh, okay. Yeah, physics, for physicists, basically Wolfram Language is the only choice among a few handful. Because for physics, physics mostly involve math, like the heart of physics is mathematics, okay, mathematical physics. So it's lots of, and mostly they have to do with the analysis branch, or also known as calculus. So calculus, differential equations, like that's a majority, like theory of relativity and differential equations, the model of the universe, and so on. GPS. Okay, so I'm gonna code. Okay, so again, this is gonna be boring. Okay, but I'm just gonna code it. Okay, so let's see. I need to grab some previous. We started in previous live stream. We started to code it. Okay, so there's a AI video summary. So let's see what I want to grab. We want to grab the code. Okay, here. So we're gonna code it for 1 hour. and I will probably not finish it, but I will try to make it a wait, not Emac this. So Wolfram Language, paste the code and pop it out. So I'll try to make it like at least part of it is done, so it can run. So but on the whole, it's not finished. So let's start to write it. Okay, if you have questions, feel free to ask me. I'm gonna code and talk. Okay, write a command to export 2D graphics to SVG. We want to do this because building export function creates huge file size. That is almost 10 times larger than necessary. Okay, that's a problem with SVG because you have so many ways to code the same thing. So it's like HTML. When you use a program like Adobe or whatever, or Microsoft Word to generate HTML, the result tends to be like bloated, like 10 times as large. That's the situation typically when you export from one format to another format in an automatic way. But if you manually, convert, then it's like 10 times smaller. So I want to do this because I have like hundreds of graphics involving two-dimensional graphics, visualization of mathematics. That let me show it again. Okay, so xali.info, my website, and go down below it's mathematics. So you go to visual dictionary of spatial plane curves, for example parabola. So there are tons of animations and illustrations about mathematics, two-dimensional. So all these two-dimensional graphics, they are very suitable for SVG. You don't want PNG because they are not scalable. Anyway, so watch my previous video, you'll see. So anyway, so let's start to write it. Okay, so we're gonna do. So for example, this is a primitive graphics. So that's a Wolfram. This is how you do Wolfram. So we don't want axis. Okay, so let's copy. Let's start Wolfram language. Okay, new buffer, paste and shift enter to run it, and move this here. And why is it taking so long? So let's make it 150. So the circle is a graphic primitives. That means basic shape. So circle centered at 0, 0 with radius 1, and then you wrap graphics around it. Then that will show us the graphics, and you add axis true. Okay, so axis gives you a sense of like what's the scale of this thing. So by default you can export to SVG like we showed this before, but so let's remove the axis. Okay, so so graphics prim. So for example, let me show this again. Okay, so do that. Okay, now it's saved in documents directory. Go there and search for circle. What did we save as XX circle? So XX circle. So you open that. That's a circle. Then show it in HTML mode so you can actually see the code. SVG is actually a XML file, so it's all text. So now you make it to be multiple lines. Replace semicolon by semicolons new line. So here's the file. Okay, so let's also make this. So here is the entire file. So now you notice, it's using the path thing. So so the file size, A69. The file size is 869 bytes, but actually the whole thing should be just one circle. Actually, I'm repeating lots of things I talked about before, but let me just do it. Okay, so if you don't know anything about SVG, you can search for practical SVG tutorial by me. on solid.info. Okay, so for a circle, you go to basic shapes. For a circle primitive, it should be a single line, so like that. Okay, so this is, that's a circle, so it should be just like 50 megabytes, 50 bytes. So let me close that. So the whole file should be just like that. Okay, but instead it creates this. It's using a path. It's using a Bezier curve. So it's trying to approximate a circle. So it's very inefficient. So when you have hundreds of circles, like I have example, like when you have hundreds of circles, then the file size is like blowing up 100 times. So that's not what we want. So that's why I'm trying to write a export to SVG function, custom function by myself, that will convert circle primitive like that to just this, instead of this. Okay, that's what we're gonna do. So let's cut that. Okay, close that. Don't save. Close that. Wait. Close. Kill anyway. Yes. Okay. So let's go back. So let me post some link here. That's a circle. Okay, actually let's not do that. Okay, so hold on a second. So this let me okay, so go back here, SVG. So let's copy the link there. That's plane curves and SVG shapes, SVG tutorial, practical SVG. So paste that actually here. Okay, today's talk show. Okay, special plane curves and practical SVG tutorial. So now we let's go back to the code. So let's start to code it. Okay, so we are writing graphics to string that turns a graphics, like anything like that, to a string, to the SVG string, and here is the SVG string. Okay, so last time we discovered there's lots of issues about scaling and about scaling the coordinate, because you have to map the boundary of the graphics coordinate. You want to find the maximum and minimum x coordinate and maximum and minimum of the y coordinate. Then you want to scale it to the pixels, because the pixel, the width and height will be fixed, like 1000 by 1000. But this image is -1 to 1, so it's just 2. So you need to scale it. That's why you need to use this view box, SVG view box, to scale it. So you need to find the scale factor and the trans vector. You need to also flip the y-axis, because in SVG the y-axis goes from top to bottom. The higher it's negative, so lower is positive. So the origin in SVG is the 0, 0 coordinate is on the upper left corner. But in mathematics, the origin is the center, so you need to flip the y-axis. So that's why you need to do this. So if you don't know, you go to my SVG tutorial. So there's a section on SVG circle, specifying style, shape style, viewport, and viewbox. So viewport specifies how many pixels, width and height. Okay, and the viewbox specifies a user coordinate. Because the actual graph may be 10 billion. The coordinate value may be a huge number, but you don't have enough pixels, so you need to rescale it. So anyway, but that's so first thing, actually the first thing when when to do this, you need to find the maximum and minimum of the coordinate. Oh Jesus, that's another issue. That's another problem, because God, every time you try to do this, you run into another non-trivial problem. Why? Because in this example, we are exporting a circle, right? So to find the maximum, the max x coordinate, one way you can do is you get all the coordinate and just find the maximum one. The x, But in this case, we got a problem because the circle, you only specify the center and radius. So you don't actually have a coordinate for the 1 and 0, So what if your circle has a radius of 1,000? 1,000 or a billion. But you won't find, so that's another problem. God. So every time we do this, we we run into lots of issues. So, but let's clarify this first, okay? So that is kind of, so now this function return a string, and here is like a sample graphics. Let's remove it, okay? And what is this? So first job, let's just write it down. First job is to find the max and min of x code and y coordinate, okay? That's in the graphics. Okay? That's the first thing we need to do. Let's do that. So what is this? So that's an example of a circle. Delete that, okay? So this is export graphics inline documentation. Let's forget that for now. Okay, so yeah, forget that. So right now we are writing this function. So so this is a simple 2D graphics of just a circle, okay? This is built-in export to SVG, okay? So now we are writing the function. So graphics to string return a string that is SVG format representing graphics object G, okay? Fantastic, that's a usage. Now, so right now it just returned this template string. So we need to, so first job to find the max and min of coordinate. So how do you do that? I don't know. So let's see. Let's search for boundary, okay? Something. Let's see if we can find a, I think there's a built-in function, BoundaryDiscretizeGraphics, okay? So BoundingRegion, okay? So there's a lot. So BoundingRegion, we can check. So if not, we might turn it to a mesh first. Okay, so this, or discretized graphics. So what does discretized graphics mean? So for example, when you have a circle, this circle, it's just represented by a circle, a center and radius. But let's say you want to distort the circle. You want to apply a function to all the points on the circle. So for every point, you want to see what is the orientation. So then they magnify the circle by the orientation. So essentially, it became a spiral. So you see, the more rotated the point is, you want to multiply that point by a larger value. So basically expand it. So the more rotated, it becomes more expanded. So it becomes a spiral. Suppose you want to apply a function to every point of the circle, okay? But you cannot do that to this circle because this circle, it's represented by just one point, the origin. So that's when you want to use discretized graphics that will break this circle primitive into many line segments. Okay, so this is part of computer graphics. Okay, anyway, I'm trying to explain, then I never start to code. So I keep this explaining. I'll never start to code. So let me see how do you find the boundary. Okay, so that's the first job. Boundary. Let's see. Bounding region. Can we bounding region points give the minimal axis align bounding a box of points? Okay, that cannot do because it takes points. Okay, so find the max and minimum of the boundary is actually necessary, so we have to do this. So we just have to first do this. Oh God. Boundary mesh region. Okay, so boundary discretize graphics. Discretize a 2D or 3D graphics G into a boundary mesh region. So yeah, so this will turn. So given a complicated 2D graphics, it will turn the boundary into a discrete graphics, okay? But okay, so boundary discretize region. What is this? Boundary discretize graphics. Okay. Okay. So again, this is probably boring. So let me just code it on my own. Okay. So we want to find the minimum and maximum of the x-axis and the y-axis. So in Wolfram language, that's called basically some kind of boundary. Get the region boundary, okay? So you want to find a command, a function that returns the min and max of the x and y of a 2D graphics. Okay, that's what we want to do. So right now we are listing all functions that contains the word bound. Okay, so that should cover all the possibilities we are looking for, I think. So there might be also max and min we need to find. Okay, so let's look at the bounds. Okay, so there are several things of interest. Boundary discretize graphics, boundary discretize region. So in Wolfram language, graphics means these graphics primitives. You have 2D version and 3D version. 2D version is just called graphics. So you got graphics. Okay, so this boundary discretize graphics applies to graphics. Now there's another concept in Wolfram language, which is region. Region is not necessarily graphics, but they are like related. Graphics can have a region, but so it's related. So region is more like a mathematical concept. So boundary discretize region. Discretizes the region into a boundary mesh region. Okay, so Okay, so you got that. We might look into, so so you need to look into the definition of region. I don't remember. Okay. Then another concept is the mesh. Okay, so this is quite complicated. So mesh is basically a mesh is just like what it sounds, like a bunch of triangles, but it also includes single lines. It's like a generalized mesh. So for example, you can look at if you look at the images, it becomes somewhat clear. So you see, it's very generalized. So you can have a mesh. This is not like typically when we think of a mesh, we think of a surface, a patch made out of triangles, right? But in Wolfram language, that's a mesh. But you could also have mesh region, and mesh region can also contain holes. And it's not just for a planar mesh, but you can also have one-dimensional mesh or three-dimensional mesh. So a three-dimensional mesh region is kind of like a box, but might have a holes in it. So so it's like fairly involved. So right now, so there are several concepts that's interesting to me. So there's about boundary graphics and boundary. So several concepts. One is discretized graphics. The other one is mesh. You can turn a graphics into a mesh. The other one is discretized graphics. Okay. Then the other concept is region. Region is like the boundary of a graphics or a mesh. Okay. Then okay, so primarily this top view is what I'm interested, I think. Okay, so let's see, what does bounds return? Bounds, system bounds. Okay, that's system bounds. Why does it? What does it do exactly? There's no documentation for interesting. Documentation web attribute protected system bounds. So why is that? So that's interesting. So you got this bounds symbol, and that's not documented. Okay, is it because we used it? No. That's interesting finding. Okay, so then you got cell bounding box. We don't care. That's kind of coordinate bounds. Okay, so that may be what we want. Coordinate bounds gives a list min max of the bounds in each dimension of the region defined by coordinates. Okay, I don't know if that will work. So the way to code this, we can start to trial and error. Just try coordinate bounds and give a graphics, but that's not gonna go well, because you're just gonna waste a lot of time. So the better approach is actually to carefully read each of the documentation. So coordinate bounds, it takes a bunch of coordinate, not graphics. Okay, so that's not good. That's not what we want. So you see, it just take a bunch of coordinates. So coordinate bounding box, min max, region bounds. So let's look at region bounds. So region bounds, region gives the bounds for the region. Okay, so but how do you turn a graphics to a region? Region bounds is also known as bounding box and bounding volume. Okay, depending on 2D or 3D. Region bounds. So region bounds returns what kind of thing it returns. So it returns like depending on dimension. For one dimension, it returns 2 points. For two dimension, it returns I think 4 points, right? So for 3 dimension, it returns 6 points, I think. So, but wait, but why is it gives the bounds for the region? Okay, so you have to think about bound region. So one dimension, the bounds is just two numbers, min and max. For two dimension, the bounds is four numbers, right? X min, X max, Y min, Y max. Is that correct though? So let's see examples. Find the bounds for region. Let's magnify this. Yeah, so okay, so let's so let's check. Find bounds for a region in R2. Okay, so you are given a triangle, then bounds, and call the function region bounds, and it returns just two numbers. Why? For a plane, two-dimensional region, it should return x min, x max, y min, y max, right? Oh yeah, so four numbers. That's right. That's right. Okay, so that's right. So this is for a plane. Four numbers. That's right. And visualize. Okay, that's correct. So it returns. Oh, so we can actually use this. Can we? So it takes a region, but a graphics is not necessarily a region. Okay, so we need to try this. So region bounds. Region bounds. Okay, is this boring for you guys? So region bounds, then let's just try the graphics. Okay, so the graphics, let's put it the graphics like that, so we even remove the primitive. Okay, okay, so you got a graphics. Let's remove the axis. Okay, so that's your graphics. Now go back here, so we can actually run this, see what it returns. Region bounds graphics is not a correctly specified region. Okay, so it's telling you a region is a graphics is not a region. Okay, so that clarifies that. But so there's a function that turns a graphics into a region though. Okay, so let's look at bounding region. Okay, so now remember, region bounds return the boundary of a region. Now in 3 dimensions, it returns 6 numbers. That's correct. 3 pairs, total of 6 numbers. X min, X max, Y min, Y max, and Z min, Z max. Okay. Now remember this function, region bounds. It returns the boundary of a region. Okay. Now let's see, what does this function do? Bounding region. Now bounding region gives a minimal axis aligned bounding box. Okay, so bounding region is basically the same as region bounds, except that it returns a coordinate in a different order, I think. Oh god. Okay, so bounding. Okay, so now I got it. Okay, so this takes a bunch of points and returns a region. Okay, so let's go back. Region bounds, right? Okay, so before we were looking at region bounds, it takes a region as input. Now this bounding region takes a list of points as input and returns a region. That's right. So if we begin with a list point, we can use this to get a region, then feed it to region bounds to get the max and min. Okay, so this is bounding region. So remember, this is bounding region, takes a list of points. Okay, but that's not what we want. We want, our input is a graphics. Bounding region is also known as an enclosing region or circumscribed region. Okay, so a bounding region R for a set of points I is region is such that so what kind of region? So you have one-dimensional case, two-dimensional case, three-dimensional case. So does it always return some kind of rectangular shape? Bounding box, yes. So it always returns some kind of rectangular shape, never a triangle, for example, like that. It always returns some kind of rectangle, okay? And it may be oriented, not just orthogonal to the axis, okay? So this is about bounding region, okay? And okay, so you can specify what kind of return shape it would be. Okay, so you got minimal disk, minimal ellipse, minimal convex polygon. Okay, so it's not just rectangle. You can kind of specify what kind of region it returns. Okay, so but again, this thing takes a list of points, which is not what we want. Or we want to be able to turn the graphics into a list of points. That I can do, but that's not optimal. So okay, so let's do. So we have to think region within region measure region bounds. Okay, so you need to turn a graphics into a region first. So find a function that turns the graphics into a region. Then you can just use region bounds region or region region bounds to get the min and max. Okay, so find a function that turns graphics into a region, or find a function that turns graphics into all explicit coordinates. For example, turn this circle into a discrete, points on the rim. Okay, so that's one thing, but I think there are a direct function that just return the boundary of a graphics. Okay, I'm pretty sure. So we want a function that directly give the boundary of a either a region of the graphics. Okay, so let's check again. Okay, boundary discrete graphics. Okay, let's try that. Maybe that's close. Boundary discretize graphics. Okay, discretize a 2D or 3D graphics G into a boundary mesh region. Fantastic. Okay, so what this do is it takes any graphics like this circle. It will discretize the graphics so that you'll get a graphics that's got lots of points on the circle. Okay, then it turns into a boundary mesh region. So it basically takes a graphics, make it into a mesh, not just the mesh, but the region of the mesh. I mean the mesh of the region. Okay, so effectively a region. Then you can use boundary bounds of region to find the maxing. So that's what we want. Okay, I know for sure. Okay, so let's just try it. So that's not right. So but that is what we want. Okay, discretize graphics. Okay, so and then what is the graphics? We can just paste that there. So the graphics is that so let's run it. Okay, let's see what it returns. Okay, that's what we want. Fantastic. So a simple circle becomes this bunch of points. Okay, then you see, then this object is a boundary mesh region. So that means we can use this region bounds to get it. Okay, so let's do let's let me just make it clear. Okay, so let me call this so that it's clear. Okay, that's graphics primitives. Let's spell it out. It's not. Okay, so now region bounds, that won't work. So but so hold on a second. So let me do that. Okay, graphics primitives, let's make it a list. Okay, typically it's a list of circles, lines, and lots of other things. Okay, then you turn that into graphics. Okay, x graphics equals to let's name these primitives. Okay, x primitives. Okay, so now x graphics equals to x prims. Okay, the result is a graphics object. Then what you want to do is you want turn that into, wait, what's going on? You turn this into boundary. Okay, boundary equals to that x graphics. Fantastic. Then you region bounds. Okay, region bounds into equals to x boundary. Okay, that is the result. So let's try that. Okay, so okay, so can we run the whole thing? Okay, let's run this in Wolfram Language. Okay, so let's paste that. Let's just run it. Okay, we got arrow. So first of all, it's a circle, a list of graph primitive. Then we got arrow. Okay, so what is the arrow? X graphics equals to x prims. Why is that an error? Graphics box is not a graphics primitive or directive. Okay, why is that? Oh, that's that. You shouldn't have that graphics there. So let's fix it. Yeah, so let's fix that. Copy that back to Wolfram Language. Select that, paste it, run it. Okay, circle, correct. That's a graph. That's graphics primitive. Then this is a graphics object. Wait a minute. Circle, that's a graphics primitive. Let's output that. Then this circle is the graphics object. That's that. Okay. Then this blue kind of thing, that's the discretized graphics. That's a region made out of the boundary of the circle and discretized it, so you can see kind of lots of points on the rim of a circle. Okay, then finally you find the boundary. So that is the boundary. Fantastic. So that's how you get the minimum and maximum of the graphics. For example, we can now we get it. Now it works, so we can kind of try a lot of other circles. For example, let's say another circle, big number, let's say random coordinate center, then big radius. Now we got two circles. One is very big radius. So let's try it, run it. Okay, two circles. Then you see one huge circle, another circle is very tiny. You can see a little dot over there. Wait, did I lose my color for my so you can see a little dot over there. Then okay, so this got fucked, this part. Boundary discretized graphics is not a correctly specified region. What? Why is that? Did I spell it wrong? No. Boundary discretized graphics. So that is a graphics. So why is it not region bounds? Oh, okay. Region bounds is incorrect. Wait. So boundary discretized graphics. So that didn't work. So the problem, because it returning it unevaluated. So boundary discretized graphics is not working. Any comments? Who's watching? Those who watches here, say hi, okay? So boundary discretized graphics is not working. So let's double check. You got list of graphics primitives, 2 circles, that's valid. You got graphics that is valid, but X boundary is incorrect. Let's see X boundary, what is the value? You see, that is incorrect. That didn't do anything. So why is it not doing anything? Is it because spelling error? No. Let's look at documentation. Boundary discretized graphics G describes a 2D or 3D graphics into a boundary region. Okay, so yeah, that's a graphics. So oh, so it didn't even need to be a graphics primitive. I mean, the argument to this boundary discretized graphics needs not to be a graphics. It can be just a list of graphics primitives. So let's try this, okay? So if you so let's copy that, do it fresh. So if you just say X prims, not graphics, okay, so we just do prims with that. No. Okay, still you see this line is not doing anything. So why is that? So now it becomes a question. So if we just the thing we are interested is just does that work? Yes, that works. So given a single circle. Now if you give a so that works. What if you give a list of circles? Does that still work? Run it. No, a list of circles fails. What the fuck? Fail. Okay, works. Okay, wait, what? Works. So let's try this again. Okay, so this is fail. Okay, yeah, so yeah. Okay, so this works. Now what about if you say graphics. Okay, so now that's a graphics object. Okay, run it. That works. So when you have a graphics object, it works, it returns the result. Okay, so that's good. So let's move that, so the input can be a graphics primitive, or it can be a graphics object, but it cannot be a list. Okay, so then why is our original fails? So you got the graphics primitives, okay, then you got the graphics object spelled correctly, yes, then you try to discretize it, x graphics spelled correctly, yes. So why this fail? I don't understand. So let's go back here. It failed because it didn't do anything. What? Graphics is this graphics, and this graphics is this prims. So it fails if you have two circles in it. Is that right? It fails if you got two circles in it. Let's try this again. Okay, let's put another circle. So run it. There, it didn't work. Ah, Jesus. So this is not hello KPTXXZ. What are you planning on export to SVG? What are you planning on exporting to SVG? Well, I talked about that in my beginning of the video and 2 videos before. So I talked about like 1 hour about it. Basically this, okay? So there are like thousands of illustrations about plane curves. That's I want to export. So today's talk show, let me remind you guys, today's talk show showing browser, today's talk show, we have 2 episodes prior, each one is 1 hour. We talked about exporting to SVG, why you need to do it, what's SVG, and so on, fairly complicated technical. Okay, so that's why we are writing a custom function. We are not writing, here is the default. I mean, built-in function, you can do it, but it creates large size. Anyway, so now back to this part. I don't really understand. Okay, so did we talk? How long have we been talking? 55 minutes already. Okay, maybe we should stop now. Okay, so we kind of made some progress. It's kind of very tiny progress, but it's solid progress because we now we have a better understanding about the different issues. Graphics, discretized graphics, what is a mesh, what is a region, and what is a bounding region, and what's the bounds of a region. Okay. It's a bit complex. So let me kind of summarize. Graphics is Wolfram 2D graphics or 3D graphics. You put the graphics into it, wrap it, it shows, graphics. All the graphics you see in Wolfram language, basically all these are generated in Wolfram language. Those are, all graphics. So graphics is made out of graphics primitives. Basically means simple shapes like line, circle, rectangle, and so on. So you got graphics primitives. Then you wrap graphics to create a graphics object. Okay, that's graphics. Or graphics 3D for 3D graphics. Okay, let me talk about. Let me go to my tutorial. Let me show you. Okay, so Wolfram Language, not math. So you go to Wolfram Language to do. No, not to do. Go to tutorial. So Wolfram Language for programmers, comprehensive tutorial for programmers from the ground up. You go to string, advanced, symbol, data structure, association, pattern matching, basics, string, comment and print, string, number, boolean, list, plot and visualization. So there, graphics, plot and visualization. So you can see, 100 plotting functions for services, for pie chart, for statistics, or 100 of them. Then you got plotting options. This is just showing you how to use Wolfram Language to create graphics. So these are 2D, and the pie chart is 3D graphics. The surface is also 3D. So then you got options such as showing axis and so on. Okay, so then you got plot 3D options, like color, lighting, very complex. It can get extremely complex. Then you got kind of the glow lighting or ambient lighting or specularity lighting specification, and you got also tone shading, so 3D coloring of the surface. Then you got also color on the surface, interaction with lighting. Also you got transparency, so very complex. Okay, so that's about lighting. Then you can have mesh data type that represent graphics. Okay, 3D graphics and 2D. So anyway, so anyway, these are about plotting, how to use the built-in function to plot, and how do you specify opacity, transparency of a graphics. So that's how to use them. Okay, that's not about programming. Okay, so once you get you know how to use some of these plotting functions, you start to do programming graphics. Okay, graphics programming. That's kind of what we are doing. So programming graphics, first of all, you need to understand about graphics primitives. So you got point, line, polygon, text, disk, circle, rectangle. That are basic primitives to build 2D graphics. Then you got 3D ones, such as also point, line, polygon, sphere, cuboid, tube, and lots of more. Okay, so graphics primitives, you have 2D primitives and 3D primitives. Okay, these are called graphics primitives. Okay, then you create a graphics object by wrapping this graphics function or the graphics 3D function, wrap them around the list of primitives. So then you get a graphics object. Okay, so there. So when the output of any graphics object shows up as a graphics like that. This is a 3D graphics 3D graphics 3D. Okay, that's a graphics object. So again, primitives, then you got graphics object. Graphics directive is like specifying color and like color, thickness, things like that. Okay, then you got geometric transformation. That's like advanced. Okay, then you got graphics complex. That's also advanced. Okay, then you got mesh region. Okay, mesh region is a representation of graphics by breaking the graphics primitive into actually points. Okay, so that's kind of another representation of graphics called mesh region. It's actually quite generalized because this Wolfram language mesh can be one-dimensional or zero-dimensional, like a list of points. That's also considered the mesh. So it's like very generalized. So you got one-dimensional mesh, like just a bunch of segments on a line. Then you got two-dimensional mesh, which is what you think of a mesh, like a bunch of triangles making part of a surface or several of them, patch of them, not necessarily connected. Then you got 3D mesh, which is very complex, which is like each mesh element is like a kind of enclosed volume. Okay. Anyway, so mesh is like another complex thing. So then you got mesh region. Okay. Which represent a enclosed region. Okay. So then you got this, convert graphics to mesh, discretize graphics. You see a sphere now becomes, you can kind of see a triangles on the surface. So that, because that's discretized. Okay. So you got discretization. Okay. So then you got the region concept. That's beginning to be what we are talking about. Then you got the boundary concept, which is the boundary of the graphics or mesh. Okay, what are we doing? So so far, how far have we go? Did we? Yeah. So that's about it. That's it for today. So today, did we understand why it doesn't work, or did we? No, we didn't get it to work. Boundary discretize graphics, but there's some. Okay, so right now what we need to do is just study this, read in detail of this documentation. I think that's it for today. Thank you guys for watching. So boundary discretize graphics. Let's see how many people are watching. I'm curious. 3. Let me make a guess. Let's see. 5 people. Okay, that's a crowd. So we did not figure out why boundary discretize graphics of a given valid graphics is not working. Okay, so right now, so the next thing to do is actually to read this documentation in detail. Okay. So boundary discretize graphics G discretize a 2D or 3D graphics G into a boundary mesh region. Okay, so it returns a boundary mesh region, which is a region that's made of mesh, and that's only the boundary of it. Okay. Then you can give an option to specify which element to discretize. Okay, so discretize full-dimensional graphics primitives into a boundary representation consisting of piecewise linear elements. Piecewise linear. Okay, that basically just means mesh. So only full-dimensional plots, area in 2D and volume in 3D, will be discretized. Okay, the graphics G can be graphics or graphics 3D or individual graphics primitives. There it is. Okay, so we give it graphics 2D, but why is it not working though? That's the thing. So this is not working. This is fail. Right? Wait, it fail. Yeah, it returns itself, so it's fail. So we give it a graphics primitive of a list of circles. That's a graphics object. So according to this documentation, graphics G can be graphics or graphics 3D. Effectively, so boundary discretized graphics effectively treats multiple primitives in graphics and graphics 3D as a union operation. Okay. Bounded piecewise linear primitives in graphics, this can be represented exactly. I don't know why is it fail. So let's try. Is it because our radius is too large? No, that's not possible. I mean, it would be very silly if the radius is large. Okay, but let's just try small just to be sure. You see, it's not doing it. It should return something like that. Okay, so Okay. Unbounded piecewise linear primitives in graphics 3D, only a finite range can be represented. Okay. So anyway, so why is it failing? So a disk, a parallelogram, a cone, discretize a cone, discretize a prism. Okay, then discretize, what is this? Discretize a whole 2D graphics scene where multiple primitives are taken as a union. Okay, yeah, it very quite powerful. Okay, but but why is discretize full-dimensional graphics primitive into a boundary representation? So is it because they are not a region, because they are disconnected, because we actually just have two let's shrink the radius. That's like kind of silly. So okay, so the, shrink, let's not to be too far apart. So now you see, two circles. Yeah, so if you run this, okay, it works. Wait a minute, it works. So when you shrink them, it works. Wait, this can't be right. This gotta be a major bug, my friend. This gotta be a major bug. If that's a bug, then I'm very pissed. Wolfram Language cannot possibly have this bug. You see, when the second circle is near the first one or much smaller in radius, then the whole thing works. You see, it return discretized. Then X boundary. Then what is the X boundary? Wait, did it return? Run it. Wait, what is the? So that's the primitives. That's the graphics. That's discretized, but there's no. Where is my X boundary? Oh wait, so there's another value, X bounds, region bounds. So paste that, that works. So let's try this again. Okay, I can't believe this won't work. Okay, so if you run this, so let's create a new section, old 4, new section, paste it, run it, doesn't work. Okay, now old 4 again, something. Okay, now paste it. Now let's shrink the circle. Okay, shrink the radius is just 11. Okay, 11, and the center is 6 and 9. Okay, do it. Oh, still doesn't work. Wait, God, what have I been doing? Why is that? What? I thought it worked here. What have I been doing wrong? Is it because I'm getting tired and is the circle radius the problem? So here the radius 6, that works. So but 11, let's change it to 6. Okay, do it. That worked. Oh god, this is incredible. So if the second radius is 11, then it doesn't work. So this is a fucking bug. This is not right. So it is possible I found a bug in Wolfram language, but this is not likely. Because how can you possibly have this bug? You see, when the radius of the second circle is, let's say, 6, then you run it, okay? Then you go down, you can see it create a discretized circle and that one, and returns the boundary, okay? So this is x min, x max, y min, y max, okay? When the radius of the second circle is 6. Now if you change it to 11, that's not a big number. Evaluate it. You see, you got this not a correctly specified region, okay? Okay, so actually, so it expects the input to be a region of some sort. So why is this overlapping circle not considered correct region? I mean, it should be a region because we have seen, you can even have this bunch of circles. Okay, that's very interesting finding. Okay, I think that's it for today. That's very interesting puzzle. I don't know what's going on, but I have, now, so I have to look into more to be sure. So, okay, I think that's it for today. Bye, guys. Shutting down in 1 minute, and I'm gonna have dinner. Very interesting. We found a bug. Seems like. So let's clarify the bug. Okay. So let me just write down the bug, the nature of a bug. Okay, seems like we found a bug. Need to look into more. Okay, and what is a bug? The bug is. Okay, so hold on a second. Let me delete this. Okay. The bug is this: when circle radius differ by just 5, it doesn't work. Okay, so this this boundary discrete graphic doesn't work. So So what works? So what works is this works. This works. This does not work. Okay, so what's the difference? So the difference here is that, so let's see what is the difference. This one, the circles are not connected. So you have, so they are disjoint. So that works, but then this does not work. In this case, the circles are like overlapping, and it didn't work, but it should, because according to this, you can even have. So anyway, bye guys. So put this back, color the syntax color it. That's today's talk show. Fantastic. Bye guys.